Hello. As we continue our study of mechanics today, we're going to look at another very important concept called the moment of force. What is this quantity? The point is that we have considered in detail the translational motion of a body and made sure that the cause of this motion is the action of various forces on this or that object. And we have found out that if the forces acting on this object are compensated or they may not exist at all, then two variants of events are possible. This is either rest of the body or its rectilinear uniform motion. If the forces are not compensated, then a certain acceleration occurs. That is, the body begins to move with increasing or decreasing speed. But what happens when the body begins to rotate? We have to guess that here too a force will be involved, but the only thing is that it will be involved in a slightly different way. It will drive the body into rotation, and here we say that the moment of force is a physical quantity that characterizes the rotational action of the force. Let's look at this with an example. Let's say we have a certain hinge. A hinge is a movable joint. So at a given point, if we fix a certain rod, then it can rotate relative to that point. Either counterclockwise or clockwise, there is no difference. So if we initially hold such a rod in a horizontal position and then let it go, what will happen to this rod? Well, it's not hard to guess, of course, that there's going to be a movement of the rod in this direction. And that movement is due to the fact that there are certain forces acting on it. And there's a point of rotation relative to which the rod can rotate. These are the necessary conditions for this motion to be created. What forces can we talk about here? First of all, it is clear that gravity will act on the rod. It's very important to mention here that the force of gravity for a homogeneous rod will be applied at the center of gravity, which is in the middle of the rod. Do not forget that the support reaction force occurs at the attachment point, which prevents the rod from moving progressively up or down. In this case, given this motion, we can say that in the vertical axis, these forces can cancel each other out. So there's no forward motion here, but as far as rotational motion is concerned, the rod starts to rotate. So the conditions have been created for this motion to occur. What are these conditions? Well, first of all, let's introduce the definition of the moment of force to understand how it works in this example. Now, the momentum of force, which is a separate physical quantity, is denoted by the letter tau and is defined by the formula. Is the product of the force by a shoulder. What is called the shoulder of a force? Well, the shoulder of the force is the perpendicular that we lower from the pivot point to the line of action of the force. But in the figure we can show these moments here to make everything clear. But we denote the point of rotation by the letter O, and relative to this point, we will consider what forces participate in the rotation of this body. We can see that in this case, the force of the support reaction has passed through this point, which means that the momentum of this force will be zero because its shoulder is zero. So, therefore, we can write that the moment of the support reaction force is the product of the support reaction force multiplied by its shoulder d1. But since d1 is 0, then this moment is also 0. As for the moment of gravity, here we have, if we draw perpendicularly to the line of gravity, and at this position of this rod, we see that this is half of its length, so the length of this perpendicular line is denoted as du. Then the moment of gravity, is the product of this force of its shoulder. And as a result, there is such a situation that this moment was not compensated by other moments, that is, it was left alone. And we can say that such a coincidence of circumstances will lead to the movement of this rod, and the uncompensated moment will lead to accelerated motion of this rod. That is, it starts to fall with a certain acceleration. At this point in time, we can then calculate it. So it turns out that if the resultant moment is not 0, then there's a certain acceleration which is also not equal to 0, i.e. there is a motion with a certain acceleration. In this case, we are talking about angular acceleration. Let me remind you that we denote angular acceleration by the letter alpha. Yeah, next, what if the force acts a little bit differently? That is, it may act, for example, not at an angle in the segment to the location of the segment in question, but at some other angle. Then, of course, we need to consider the components of the force which will be at the right angle to the given segment. Let's take an example of this. Let's say we have a certain body and it has a certain point of rotation. A certain point of rotation O. So the body can rotate about that point. And we can apply forces in different directions. Let's say in this format, let's draw a picture. In this case, how can we correctly show the shoulders of these forces? Once again, I remind you that the shoulder of a force is a segment that is perpendicular to the line of action of the force. To do this, we must draw the line along which the force itself acts and drop a perpendicular to it. This segment will be located at right angles. In this way, we obtain the value of the arm D1. Do the same for the force F2, and we get a shoulder for this force D2. Thus, there are two moments that rotate the given body. Here it's important to realize that it's possible that the forces will rotate the body in one direction, or maybe they'll rotate it in different directions. In order to correctly determine the direction of rotation, we're going to compare the direction of rotation of the body to the clockwise motion. Let's draw on our drawing where the clockwise hand moves and see in which direction the given forces will rotate the corresponding bodies. So we've got the clock hand moving in this direction, and it turns out that if you shrink it down a little bit, the circle of rotation of this arrow, so if you show it like this, we see that the force F1, its direction of rotation coincides with the clockwise arrow, so its direction of rotation will be clockwise. The momentum of such a force is considered to be negative, but this is such a convention and the sign is corresponding, so let us write that. Minus tau 1, that is minus F1 times D1. And we look carefully at the force F2, that is, if we twist the clockwise arrow, we see that here we have the arrow going up and the force is acting down. So it's directed, its momentum is counterclockwise. So T2 is F2 by D2. Well, the resultant moment respectively will be the sum of these two moments. Again, depending on the situation, it may or may not be zero. In any case, you and I realize that for this situation, given the calculation of the resultant moment, we can also use Newton's second law of Newton, which says that the resultant moment of all the forces acting on this body, it determines the acceleration with which this body will move. And the coefficient of proportionality here is the moment of inertia, which is the value that's responsible for the inertia of this object. We've already talked about this law. And then, depending on the task, we will consider different situations and see how the moment of force is calculated and the consequences that it ultimately creates for the body. That's the end of our lesson, and we'll see you at our next classes. Goodbye, everyone.